All right. Good afternoon, everyone. Welcome to the CISER seminar today. This is the second seminar we're having in this fall. I hope your semester is going well. We are approaching the middle of the semester, and I hope your midterms have gone so far well. We kicked off this season just a week ago, and we have another one today. And from next time on, we'll come back to our regular schedule and have the seminars every other week. But today we have a great pleasure to be hearing from Dr. Mohammed El Mahalawi, and he's going to make us stare up into the space. And his seminar is titled in an intriguing way, Does Space AI Security Matter? Is what it is titled. And Dr. El Mahalawi is a new assistant professor at WSU, joined just this fall. He's located in the Tri-Cities campus, joining the cybersecurity program there within the computer science and cybersecurity department. He comes with very interesting background. He has both computer science, computer engineering, and electrical engineering. His PhD is in computer science from Missouri University, Science and Technology, which he finished in 2024, and he has a master's in computer and electrical engineering from University of Rostock in Germany. And his research is at the intersection of AI and cybersecurity, and works on things that are associated with privacy preserving things. And so federated learning is one of the areas he works in. And he is teaching an introduction to machine learning course in the Tri-Cities campus this fall, and has got a growing group, I know, and is hiring PhD students. And so we have interacted since he came to WSU, and very energetic and having multiple things that he pursues, both in cybersecurity and outside. And so we'll talk today about his work in federated learning that involves satellites. And the way we will do this, just as we usually do, is let him have the time to discuss, and I hope he will leave some 5-10 minutes towards the end for discussion. So if you have things that you would like to ask, you can put them in the chat. James and I will be monitoring them, and we'll ask Mohammed at the very end to address them. And there will also be a chance for you to give feedback, and so there will be a link that you would get be alerted to 5 minutes or so towards the end. Please take the time to complete that and make sure that your participation is noted. With that, I think I would just let Dr. El Mahalawi start his seminar, and welcome to CISER, and take it away.
Thank you so much, Dr. Asif, for this great introduction. Because we just are running out of time, I have to start as soon as possible now. Today I will discuss what is the privacy preserving related to federated learning when it comes to low Earth orbit satellites. But before we dive in, let me go step back and introduce to you what is low Earth orbit satellites. So recently we have seen surge of interest from giant companies and even government for launching a huge low Earth orbit constellations. For example, SpaceX have their own constellation or satellite network, and also which called Starlink. Another big player in that domain is Amazon, as they also have their own constellation, which Project Kuiper. Now, also OneWeb is another giant company that will start to launch a huge amount of satellites into space. In terms of government, we can think about NASA. They have also their own satellites, and European Space Agency. Those are the most players in order that are interested in launching a huge constellation for low Earth orbit satellites. Low Earth orbit satellites have many applications. Due to their very small size, and they just are flying very near to the Earth, just around 1,000 kilometers from the Earth, they can capture very high resolution images. And these images can be used for many applications. We can consider one of the most important applications like border monitoring. The government itself can use just the collection of the images to see what is going on their border. Another attractive application is disaster detection. we can collect some images related to what is the disaster, when, and how can we localize this disaster in real time. In fact, those satellites can collect a huge amount of data every day, which might be reached to 5 petabytes of images, as reported by 2019. So traditionally, those satellites just transmit the images to a ground station for training a large-scale machine learning model. But in fact, this is not the ideal case because we have some privacy and security restrictions on downloading such raw images. In order to see what it actually means, for example, if some satellites collecting their data and just transmitting this data to a ground station, an observer can be in the middle and just can take those images and retransmit some fake images to the ground station. So if we just transmitting the data without caring about their privacy, we will have some big issues in terms of security and privacy preserving. So man in the middle is usually a problem in traditional communication. But what about low Earth orbits? And in fact, we will discuss more advanced security threats that we can have in such a low Earth orbit network. Another and the most important challenge is efficiency. We have mentioned in the previous slide that satellites collect around 5 petabytes images per day, but the available bandwidth is only around 50 to 500 megabytes. So downloading such a huge amount of images with this kind of limited bandwidth is also a big challenge. On top of that, satellites or low Earth orbit satellites have sporadic and irregular connectivity, which means each satellite can only communicate with the ground station few times a day, around 10 times, and each time the communication will be around 5 to 10 minutes maximum. Meaning that how can we send a huge amount of data with that limit on the bandwidth within just a short time? However, in our today talk, we will just focus more on the privacy and security aspects, and maybe later we can discuss other efficiency challenges, how we can tackle them. So one of the consequences of just not downloading images in real time and try to detect what is happening on the Earth, especially if this is area in a rural area or some area we cannot reach it. As reported in 2018, in California camp, there was a forest fire, and due to the lack of downloading images, just 4 hours delay causes around burning 140,000 acres, and at least 56 people got killed. So the problem is how we can utilize these images, but not just 4 hours later, how we can utilize these images on real time. One of the solutions to this big problem is what about just introducing the concept of federated learning to low Earth orbits? What is the federated learning in general? So in federated learning is just a new developed technique with the aim of preserving the privacy of the images. So each satellite will just collect its own private data, and instead of downloading or sending such data to the ground station, the satellite itself will start to train a machine learning model on board. And once all satellites in our constellation that might consist of thousands of satellites train their models, they will send their models to a ground station. And this ground station will start to do something called aggregation. So the ground station will just aggregate the model weights. And after aggregating the model weights, they will generate a new model which is called global model. Once the ground station generates such a global model, it will send it back to the satellite for another round of training. However, It looks like it's very easy, very simple, but when it comes to satellites, it is not such simple when we are talking about any IoT system. As you can see, this operation is just will be back and forth between satellites and the ground station. So this is one of the challenges that we face. And also we mentioned that we developed the federated learning in order to preserve the privacy of the images. The question here, whether that approach really preserves our privacy of the images. In order to be more focused, let me introduce what will be the actual challenge in such system. So the most important challenge for us is that privacy and security threats. We mentioned that we will transmit as our models instead of data, which is correct. However, these models is still transmitting over insecure communication channel, meaning that if there is an eavesdropper or any type of attacker can just steal this model and apply some advanced attacking system called attack system called model inversion attack, just engineering reverse attack. If I have the model, I can regenerate the original image again. So sending the model itself, we found that it cannot preserve the privacy of the image because models still have some features from the original data that we will able to reconstruct them again. Also, we mentioned that we have limited computational and storage on satellites, meaning that low satellites in fact cannot train a large-scale machine learning model, which means those small satellites that have only 10 by 10 by 30 centimeters, they have very, very limited GPUs or CPU. How they run large-scale machine learning model, and in fact, as we are computer scientists, most of us saying my model needs 1 day, 2 days, or even more than that in order to be trained. So this is a big issue when it comes to also satellite communication. However, this is also for today, this is out of the focus, but maybe I will discuss it in other talk. Third, the sporadic and irregular visibility pattern. In case we mentioned the communication is just traveling back and forth between the satellites and the ground station, which means in order for the global model to converge, which means achieve good accuracy on their classification, it still needs days or even weeks for model to achieve convergence. But for today, we'll just dive in what is the privacy and security threats and how we can defend such privacy and security threats. But before we go to this step, let's let's discuss what is the main difference between privacy and security. Usually people say privacy security, but are these two words mean the same? In fact, privacy and security are intertwined, but they are not same. What does it mean? Privacy just aims to safeguarding the personal data. We need to make sure that our data is already encrypted, we can no one can understand what is the data that we are trying to transmit, which is something we already done by applying federated learning, because we convert the data into machine learning model. In terms of security, we need to make sure the data integrity, meaning that if we're transmitting some data on the communication channel, maybe the attacker will steal this data and take just a copy of this data and send it back to the ground station. The data is already stalled, but no one knows what is happening. So we need to check what is the data integrity. Is someone manipulate this data or just have different version of this data that we have? So one of the methods to defend or to ensure the privacy is applying an encryption technique, or just decrease the amount of the data that you are being transmitted on that communication channel, Or you might just care about data anonymity by just sending some representation of the data, which is, we can say in our scenario, will be the machine learning models, not the data itself. Another way also to control to defend for the security or ensure security, that we can have an access control. We make sure that the transmitter is the correct one, not just someone in the middle. Also, we need to think about verifying the information or authenticate the information. The common thing between these two, security and the privacy, is both of them are caring about protection of personal data. We mentioned here verification and authentication, but what is also the difference between verification and authentication? So, in order to build a strong system, it should, number one, preserve the privacy of the data, ensure the data integrity, and ensure the data integrity relies totally on verification and authentication. Let also give me some brief overview about authentication and verification. In terms of authentication, they also look similar, but they have different but they serve different purposes. For example, the authentication, it is used to confirm the user identity. Who are you? If I am the sender and I send the data, I need to check whether I received this data from the sender that I expect to receive the data from. They just check whether satellite number one, who he is actually send the data, or maybe someone in the middle steals the data and send it back to the server. Even the one in the middle didn't change the data, but still he has a copy of this data. So in order to do that, we have to check who are you. The second one is the verification. Verification cares more about the data itself. If I am someone, or I am someone in the middle who steals the data, but he manipulates the data and send another version of the data, then we are caring about verifying whether this data is correct or not. So it just care about the data that being received by the ground station or by any server. Again, a way to make sure that we have a good authentication or defend regarding authentication, we can just have access control, user identification, and also user trust. The second one of verification, and even for verification, all of us can see it today for the or two-factor verification that we usually used in order to open our private emails. Most of companies start to have multi-layer of those verification and authentication. Another one is data consistency. We need to make sure that the data that we received is the data the sender already transmitted over the channel. And also we have to validate the data somehow. So the intersection between the authentication and the verification, both are comes from security perspective, to add more security layers in order to make sure our data is not tampered with or not manipulated during the transmission. So in order to develop a secure and privacy-preserving technique to preserve the data that's being transmitted in our communication, we have to achieve both privacy and security. But what actual threads that we have here in terms of federated learning with low Earth orbit satellites? We can divide them into three main segments: satellite, space segment, and communication segment. Then we have ground segment. In terms of a space segment, we can just see some threads like command intrusion, payload control, or even poisoning the satellite itself. In terms of the communication channel or communication link segment, we can see the data stealing, data manipulating, reply attack, impersonation attack, and so on. Anyone steals the data in order to manipulate it. In terms of the ground station, we consider it as traditional network because ground station can suffer from traditional attacks that we already know, hacking, malware, and cloning. In the system we develop, we will try our best in order to keep all of those three segments are secure and also keep the privacy of the data being transmitted. So again, we mentioned right now that we, instead of transmitting images, we will start to transmit models. Consider the satellites now can run machine learning models. Consider this problem is already solved somehow. Now consider again satellite can run can utilize its collected images and train a machine learning model. The second step during the transmission over insecure channel, and if the dropper will steal these models and apply some inversion attack to reconstruct the original model again. So that's why we cannot trust the federated learning by default, because we found that transmitting models is still under attack by some advanced techniques. And I might not just cover the one on the ground station. As the security on the ground station, once it receives the data, it just has to make sure the data I received is correct, verify it first, it check its authentication and stuff like that. But we consider the ground station itself system is secure. What adversaries that we consider in our problem? We consider several adversaries, starting from outsider adversaries. Outsider may be passive attack. Passive attack means I am on the communication channel. I will just steal the model or steal local or global models for some malicious purposes. However, I will not change the model. I will just take or steal a version in order to use it for some malicious purposes. For example, we can see that called reply attack or impersonation attack. We also consider the active attack. The active attack will steal the model, manipulate those models, and send another version of those models to the ground station. He might just need to introduce bias to the global model. I need this model just to give good accuracy on identifying disaster, but this model will not able to classify or identify anything what will happen on the country border. So we need to make sure this is also tackled in our system. It might also have some purposes on just hindering the convergence of the model. Such attack called the model integrity attack. We also consider insider adversaries about the satellites themselves and the ground station. We consider that we are working with honest but curious. It means satellites and the ground station are honest. They will follow the FL principle honestly. However, they have some curiosity to learn or infer some information about others. In fact, when we're talking about federated learning, we are not just talking about one company like SpaceX and the ground station. We are talking about SpaceX, Amazon, and even OneWeb company. All of them are working together in order to develop one global machine learning model. So it might be some of these companies wanted to know what is the data collected by other companies. So we also need to stop that action or to just consider it. Otherwise, some companies, they mentioned, we will not join such a training because our data will be under attack. Another part, as I mentioned, called colluding. One vendor can collude with the server in order to get information about data collected by another vendor. Let's discuss our first solution, which called secure aggregation. So traditionally, I like to discuss those stuff based on the math, but today I will discuss them from very high level So I will just give you the concept and what we actually did. But I need to be simple so that anyone can understand what is going on here. So consider that we just have some ground station is located somewhere, and many other events is happening around this ground station. Some satellites within a certain orbit will start to collect their data. So the satellite will start to send its waves in order to capture some images related to the ground station. And after that, each satellite will start to, after the collection of the data, each satellite will start to train its machine learning model. In order to develop a secure aggregation technique where nothing can be leaked of the private data, we have to encrypt that model. So what we did here, actually, we just developed the model using an encryption technique. And what is one of the difficulties that we faced here, that we have to develop a lightweight encryption technique. Why we mention lightweight? Because satellites have very small computational capability, which means we need to make sure that satellite will able to encrypt the model with its own limited computational capability. So after that satellite, which was visible to the ground station, generate its model and encrypted it. Also, we will wait until others, this called secured partial model, as we will just generate one model per orbit. The same process will be happen for all other satellites from different orbits. So other satellites will do the same job in order to collect their data and develop models and encrypt their models. Once all satellites finish their training and encryption, satellites will start to have their private keys. However, these private keys that used to encrypt will not be shared with the ground station. This is one of the advantages that we introduced here, because traditionally we have something called key distribution center. We consider we have a center on the earth. This one is trusted. However, this center should know all the private and the public keys in the system. But in our case, private keys only knows by satellites in space. The ground station knows nothing about their keys. What will happen next? The second step, those satellites will start to transmit their encrypted model to the ground station. The ground station next will just aggregate those encrypted version of the model in order to generate secured global model, not a global model, but it will be secured global model. After we generate such secured global model, we will send it back. Yes, one comment here. We have to know that the ground station does not have secret key. They can just do some operation on those encrypted data, which the method we used it called functional encryption, meaning that the ground station cannot decrypt the received model, but can just do some mathematical operation on those models. After the ground station generated such a secured global model, it will send them back to the satellites for retraining. And this process will be going back and forth until the global model is converged. So let's repeat this stuff in just some certain bullets in order to make sure that our message is delivered. So the methods that we use to tackle privacy, we just encrypt the satellite's models using a lightweight cryptography technique. Also, we use an anonymous veto protocol in order to generate those public and private keys in a decentralized manner. Decentralized means each one who knows its key, but nothing about other satellites in the network. Also, we tackle the security concerns in two ways: before aggregation and during aggregation. What does it mean before aggregation? Once here the ground station receives the encrypted model, first it has to check their verification and make sure those models are not tampered with or manipulated during the transmission. In order to do that in our system, we use a timestamp. So if the encrypted model received by the ground station after a certain time, then it will be considered as not manipulated. But if this time increased on a certain limit, it means an attacker steals the model and send it back. So we have to check first and verify those models are the ones that we already interested in and they are not manipulated. What about during the aggregation? During the aggregation, we use inner product functional encryption. As I mentioned, the ground station at this point will not able to decrypt the
You got muted, Mohammed.
Can you hear me now?
Now you're back.
Okay.
Yeah.
Some advantage from here or from the beginning?
No, you're fine. Just continue from here.
Okay. Some advantage that we mentioned here that we are not using any key distribution center, and also we didn't make the big assumption as others usually consider at the beginning we should have some secure channel. Why? Because during the secure channel we can transmit those public and the private keys. Even this assumption looks fine for traditional IoT system, but when it comes to space, this secure channel, it's very hard to ensure between ground station and satellites. The second part here is the maximum now that the aggregator server can do is just to calculate the aggregation sum, revealing nothing about the private data or private models of individual satellites. Also, we check the integrity of the model. We make sure that this model is verified and is not tampered with. And we achieve less computation and communication overhead. Another thing here I have to mention is some results regarding privacy and security. We compare our approach with one of the approaches from literature called threshold homomorphic encryption. We measure the computation overhead and we found that we can just generate our keys in 1 millisecond while other needs 22.3 milliseconds. In terms of communication overhead, we measure it using the message size that we are transmitting. We found that our approach just can send 1000 megabytes while other need 39 megabytes, which means we reduced the communication overhead by 39 times. In terms of accuracy or convergence, we also test our approach on a realistic data set called the Deep Globe for 7 different classes. Here is the original image and the ground truth label, and this is what we predicted. As you can see, in the prediction, it looks like similar data, the similar ground truth, which is higher accuracy. And also we can see if there is a fire in the original image, our scheme is still able to detect there is a fire in that area. And note that this is the result after only 3 hours of convergence. However, we can achieve much better result if we still continue the training process. Another problem that we solved called long-term privacy. So we now make sure that secure aggregation will work. We can encrypt and make sure the privacy of our scheme. However, we uncover that secure aggregation approaches are myopic and even may fail against some strategic intruders. In other words, secure aggregation can only protect for a single federated learning ground. But when it comes to multi-federated learning grounds, it may fail. In order to understand this scheme, let's start with a simple example. Consider that in the round 1, we have device 1 and device 2 are sending their model, then the ground station will have W1 plus W2. In the round 2, consider device 1, 2, and 3 will send their model, then the aggregation will be W1, 2, 3. Similar for another round, consider device 2 and device 3, then we will have W2 plus W3. What will be the issue here? The ground station already have W3, W2, W1, which called the global models. By doing some simple math, we can actually just subtracting this global model from the previous global model so that we can reconstruct the original local models of such satellites. This is a big concern because if the ground station is just still keeping the model or saving the model over the long term, it means by certain rounds the ground station will able to reveal the original data. So applying some model inversion attack on such data, then we will just have again a private data reconstruction. We need to stop such attack, or not attack, we can just say such myopic strategic intruders. In order to do that, we develop or we define long-term privacy. We need to keep the privacy even if the ground station can store the model for many several rounds. The ground station will not able to understand any of such data. For that, we develop this scheme called LTP FLEO, which consists of 3 main components. I will try to speed up because I think I'm running out of time. So the first one is called privacy-aware satellite grouping. So instead of allowing each satellite to send its model, we will start to group the satellites based on their availability. And we will allow satellites to, we will allow the ground station to aggregate models together or not to aggregate them at all. For example, if the ground station receives only satellite 1, it will not do any aggregation. In order for the ground station to start the aggregation process, it should receive the data from satellite 1 and satellite 4 together. Similar for satellite 3 and satellite 5 and so on. So the idea here is not allow the ground station to work on individual local data so that the ground station cannot reveal any of such individual data. We just calculate the probability of satellites K to be visible because we need also to care about convergence. So we make sure that satellite 1 and satellite 4 they will usually visible or can communicate with the ground station within the same time period. Then we allow just the ground station to do some partial sum of the satellites model so that it will be unable to decode any individual models. The second component called model age handling. Why we called it age handling? Because we found even that first component will ensure the long-term privacy, we still have an issue. Comes from some satellites will send a fresh model that just currently trained on the global model, while others they have some stale models. And if we aggregate some model with old weights and another model with updated weights, it means the global model convergence will be degraded. So we need to avoid such degradation in the accuracy. In order to do that, we just care more about the participation frequency of each group. If the group of all satellites in group 1 participating regularly, then we will just keep them in the aggregation process every time. In order to do that, we just did some constraint about who should be participate using some tolerance factor, meaning that only satellites that they have a high number of visibility or communication with the ground station, they will only be allowed to participate. This way, we make sure that the model will be converged at a certain point. However, solving that problem, it also comes with another problem. Because if you are only consider the only updated models in the aggregation, it means you are discarding some other data or some other models that might be very important as well. So it causes a biasing problem, and that's why we come up with the third component in order to tackle such biasing component, such biasing that we have. So our aim is just to prevent biasing the global model to a certain class or to a certain data collected by the most visible satellites. So what we did, we calculate the fairness gap, which will be what are the maximum participation of each group and what is the minimum participation. We need this fairness gap in as much as we can to equal 0, so that we ensure that the maximum participation equals the minimum participation. In order to do that, we just multiply with some weights. We add small weights for outdated models and larger weight for fresh or regularly updated models, as we can see in such equation. In terms of results, we started with different type of group sizes. One group has only 2 satellites, another has 4 or even 6 satellites, and we start to apply model inversion attack to such a group. As you can see that in that figure, this is the original ground truth images. And this is just the reconstructed images after without using our approach. After the ground station just save some global model, it will able to reconstruct the original images, and you can see this is considered as very high accuracy. When we start to use our approach that will only use a group size of 2, we see that the accuracy of the prediction started to decrease, which is our target. Increasing the group size, it will also provide better results until we achieve what we are looking for. In terms of some other quantitative results, we just show that our approach can achieve high accuracy or less accuracy compared to other approaches without caring about the long-term privacy. And this actually decreases by increasing the number of satellites within the same group, which is increasing the size will 100% increase the against any reconstruction attack, but at the same time we found that this will affect the convergence rate. Also, we tested on another dataset called EuroSat dataset, and we show that out of 5,400 samples, we only one image got misclassified, which is very good result. In terms of comparing with the state-of-the-art approaches, we found we usually have the best convergence rate. However, our convergence rate started to decrease by increasing the number of satellites per group. These just results on different kind of datasets. Lastly, here we also show some results on different communications perspective when we just change the constellation inclination. However, this is not something related very much to security. It's just related to convergence. We show that even the inclination is low, we're still able to achieve good accuracy. And here's the confusion metrics showing that all the correct classification is high, even we are preserving the privacy over the long term. Also, we moved from such working only on developing some simulation. We have already started to test our approach on a real satellite systems that developed during my previous PhD at Missouri University of Science and Technology. We tested a very simple approach on a Raspberry Pi. And as you can see, we already launched these satellites into space this year on March 6th. Um, and also, you can see in the future, we have a plan to submit some other satellites in 2026 with a collaboration with my colleagues in Missouri. We will launch two satellites, one of them called Missouri Rolla and the Missouri Rolla Second. We called them Mr. and Mrs. And they will be equipped with Jet Nano that we are working on testing our developed approach on it right now. My take-home message is AI-driven satellites is coming in the near future, and security and privacy risks can be addressed in terms of the space using such decentralized secure aggregation and privacy-aware schemes. Also, we can achieve high convergence and achieve high acceleration in terms of the convergence and ensuring security and privacy as well as fair aggregation. And that's all that I have for today. I hope that I didn't exceed the available time.
No, you did a good job, Mohammed. Very fascinating talk, interesting work. Thank you. We have a few minutes for questions. If somebody could, or if you have questions, you can ask. And James, I probably would like to remind you to put the link for the survey. So we've got a couple minutes for questions. Anybody has got, you could unmute yourself and ask, or you could write down your questions on chat. Maybe while somebody thinks of a question, Mohammed, I want to ask like just more curiosity question. With these satellites, the image portion is quite clear to me. Like they can take images and you could use them, which is what many of your experiments also show. But what else can you get when you have satellites? What sort of information can you get other than images from them?
Most important data for satellites that I'm working on right now is the communication signal. In fact, satellites are developed for global internet coverage. So usually those published by SpaceX, the main target is to provide coverage. As we can see in Ukraine war, SpaceX just started to provide them with internet at that time. And even it has reported last year that Russia did cyber attack on SpaceX for one whole day. And within a whole day, SpaceX wasn't able to control their satellites in space. However, they just start to do some software updates in order to defend for such attack. So this research is going mainly on the communication, not only images. And one downside that the military communication here in the US based on 80% of the commercial satellites. They didn't launch their own satellites. They are using satellites by different vendors. So we still need to ensure the security because we are relying on different vendors.
Mm-hmm. I see. How much of, for students who are following now, how much of this is a good example of you have both electromagnetic spectrum and cyber, which is where the communication would come. How much of knowledge, fundamental knowledge in communication do people need in computer science need to have to secure systems like that? Is the communication knowledge crucial to the technology developed in terms of secure and privacy preserving solutions?
In terms of the communication background, we will just focus on traditional communication system because the main target is to preserve the privacy. So whatever we have in communication, we consider it is something for granted. What I did, actually, I was using a simulator called STK, and this STK will do all the communication purposes. I just need to collect what the communication time, how many minutes the satellites will be visible, which is the most important information from my side. But maybe we can extend it to focus more on communication itself. However, I just consider the communication signal is something for granted as for now.
Mm-hmm. There's a question Christopher is asking on chat. If you see it, I'll read it out so that others can hear too. When increasing the number of satellites using either strategy, the strategies you discussed, you still encounter diminishing returns you mentioned. Does the data also suggest that we should be segmenting our ISLS instead of creating a global network? And what does that mean for satellite privacy?
Yeah, first of all, he is asking whether is it better to transmit the data directly to the ground station or just use the inter-satellite link or the communication among satellites, correct? In fact, the only one that has right now inter-satellite link or the communication between satellites in space is SpaceX. Other companies that does not have these options yet because their launched satellites was a bit older than the SpaceX. So we cannot rely 100% about there will be a communication among satellites. And even this something will happen. Satellites owned by certain vendor might be not willing to communicate with satellites owned by other vendors. On top of that, the communication in space between satellites from different orbits, it's very difficult because those satellites are traveling with very high speed. So communication will be suffering from something called Doppler shift.
Great. We have run out of time. I could have asked more questions. I got very curious about many of these things. I'm sure the students are too. But we'll have to stop it here, and maybe we'll have you another time with more details, or even in the summer workshop when we run it. But thank you very much for taking the time to share your work with us today. And thanks everyone for attending. Those of you